Okay, in this screencast, we'll continue our discussion of two-dimensional Haar wavelets and talk about tensor function products and two-dimensional Haar wavelets. Let's start with a few basic definitions that we will use in the rest of the screencast. So given two functions, let's say f1 and f2, and these are some arbitrary functions. So the tensor product of this function, these two functions, defined as formally is defined as f1. Then there's this tensor product sign, f1. Well, we're going to say tensor times f1 tensor times f2 of xy is just going to be a product of f1 of x times f2 x f2y. And then we're gonna one way in which typically a transition is made from one dimension to two dimensions, not just in Haar wavelets, Haar wavelet analysis, but also in other types of wavelets, is that you have a wavelet or step functions for one dimension, and then we use those functions in the horizontal and the vertical dimensions to define two-dimensional Haar wavelets. And so you have the phi step function that we have used in our Haar wavelet analysis, one-dimensional Haar wavelet analysis, and psi function, and I will be calling them small phi and small psi for the remainder of this screencast, and they're defined as follows: phi of x from 0 inclusive to 1 exclusive is 1 if x is less than or equal to 0 and less than 1, and so forth. So and then psi, and then psi, small psi. So we can use these two functions to define two-dimensional Haar wavelets. Then the first one is the so-called average or constant wavelet, defined as big phi, and 0, 0 is essentially the coordinate, the origin of our coordinate system. We can obviously define it as x and y arbitrarily. The origin is rather arbitrary, and the superscript of 0 just means that there is no change, right? It's a constant wavelet, and is defined as the tensor product of phi and phi, small phi and small phi of x and y. And so graphically, so this is we drew the y-axis and the x-axis, and this is our origin 0, 0, and this is our 1, 0, and this is 0, 1 on the y-axis. Okay, and this is 1, 1. Okay, and so if we work out the value of this tensor product at each of these 4 corners, so this is phi, big phi of 0, 0 is equal to the tensor product of small phi, the interval from 0 to 1, 0 inclusive 1 exclusive, and phi from 0 to 1, 0 inclusive 1 exclusive, 0, 0, and that's it's 1, 1. It's going to be 1, 1. So if we work out the big phi of 0, 1, we're gonna get also 1. And phi, big 5, 0, 0 at 1, 0 will also be 1. Okay, and then finally at the fourth corner of 1, 1, phi sub 0, 0 at 1, 1 will also be 1. So, and everywhere else in this cube, the value of this tensor product will be 1, so we're going to get this cube. Okay, so then we can define a two-dimensional horizontal wavelet. So let's say big psi, right? It's h is horizontal, right? And then it's at 0, 0. At xy is defined as the tensor product of phi on the interval from 0 inclusive and 1 exclusive. It's tensor times and psi on the same interval of 0 inclusive and 1 exclusive. Of x and y. Okay, and that's equal, and that equals phi on 0, 1 of x times psi 0, 1 of y. And it'll be 1 if x is greater than or equal to 0 and less than 1, and y is less than or greater than or equal to 0 and less than half, minus 1 if x is greater than or equal to 0 and less than 1, and y is greater than or equal to 1 over 2 and less than half and 0 otherwise. So graphically, this wavelet can be defined as follows. So you have our origin at 0, 0, then the x-axis and the y-axis. So that's the middle is the intervals on both axes are from 0 to 1. And this time we will have to draw the z-axis. This will be our z-axis, and the z-axis will be from 1 to minus 1 with 0 in the middle. So this is 1, this is minus 1, 0 in the middle. So let's just write that this is the z-axis. Okay. All right. So at 0, and this half, this will be the value of this tensor product will be 1. And by the way, this tensor product, what is the horizontal two-dimensional Haar wavelet measures? It measures the change in the data from the left half of the data, and of course the size of the data is an integral power of 2, to the from the left half of the data to the right half of the data. So like if we have let's say an array 2 by 2, right? So it'll measure the change from the average in the first column to the average in the second column, for example. And or perhaps in the next screencast we'll go through a concrete example where the two-dimensional Haar wavelets are applied to some simple array, two-dimensional array of values. Okay, so this is that's what it is pictorially, right? This horizontal wavelet, and in terms of matrix representation, for example, it's 1 1 and minus 1 minus 1. So the change from the left to the right. Then the two-dimensional vertical wavelet is defined as the big psi. So V 0, and then the origin at 0 0, because that's the origin. It can be arbitrarily chosen, and the big psi is defined in terms of small psi on the interval from 0 to 1, 0 inclusive, 1 exclusive, tensor times phi on the interval from 0 to 1. So this is the vertical change. So if we can work it out, it's phi of x times psi of x, and the values will be 1, minus 1, and 0. So this takes the value of 1 if x is greater than or equal to 0 and less than 1 over 2, half. And y is greater than or equal to 0 and less than 1. Okay, it takes on the value of minus 1 if x is greater than or equal to 1 over 2 and less than 1, and y is greater than or equal to 0 and less than 1, and 0 otherwise. Okay, and pictorially, again, this is our origin. We'll keep the z-axis, right? That goes from 0 or from 1 to minus 1 by way of 0. And this is our x-axis. This is our y-axis. And this is 0, 1. And this is 1, 0, 1, 1, right, rather. Okay, and so then we'll mark half on the x-axis and half on the y-axis. So in this rectangle, right, rectangular cube, we can say, the value of this wavelet, big psi, the vertical rather, will be equal to 1. Okay, and this interval, the value of that's the second, right? This like if x is greater than or equal to and that's this case, if x is greater than or equal to 0 and less than half, and y is greater than or equal to 0 and less than 1, right? And then we're gonna draw the second case where x is greater than half, less than 1, and y is greater than or equal to 0 but less than 1. So it will be sort of this cubic form of height 1 but going down, right, with the rectangle where x is from half to 1 and y is from 0 to 1, right? Okay, so then the vertical change essentially marks the change from the upper half of the data to the lower half of the data. And then finally there's a diagonal change, which is defined as, well, let's draw this first. Okay, again, this is the origin, okay, y-axis, and then coming down to the point 1, 1. Okay, let's mark half on y and x. This is x, this is y, and okay, so the diagonal change will be we'll have the value of 1 in the upper, in the top left corner, right? And we'll work it out momentarily in terms of symbols why that is the case. Okay, all right, and then so this is the big psi diagonal at the origin of 0, 0 at x and y. It's equal to tensor product of the small psi on the intervals from 0 to 1, tensor times small psi, the interval from 0 to 1. X and y. So this is psi of x times psi of y. Okay, and so if we work out all of the cases, the value of the diagonal wavelet, two-dimensional diagonal wavelet, is equal to 1 if x is greater than 0 and less than half, and y is greater than 0 and less than half, which is what we drew with that blue, small blue cube. It's also equal to 1 if x goes from half to 1 and y goes from half to 1. All right, this is it. It's an essentially 1 in the bottom right quadrant, right? So this is also 1. Okay, and in the other two quadrants, right, the bottom left and the top right, the value of this wavelet will be equal to -1. Okay, so this is let's formally define this. And essentially, what does the diagonal wavelet measure? It's the change between the two main diagonals, right? The change in data between two main diagonals. So the average along the first main diagonal from the top left to the bottom right, and the average along the second main diagonal from the top right to the bottom left. So that's what these tensor product, the tensor product that defines the diagonal wavelet, two-dimensional diagonal wavelet measures. Okay, and then that's the top right cube, also going down because the value of the tensor product is -1. Over here as well. Okay. So, and then it's 0 everywhere else. Okay, this is to be continued.